Hello viewers, today I'd like to discuss about the nature of the roots of a quadratic equation. This is the problem that we are planning to solve. We need to show that the roots of this quadratic equation, that is a squared plus b squared times x squared minus twice of b times a plus c times x plus b squared plus c squared is equal to 0. We need to prove that the roots of this quadratic equation are real if and only if b squared is equal to a into c. That is, a, b, c are in geometric progression. We are given that a, b and c are real numbers. Now, the basic background knowledge that we need to solve this problem is this. Let's look at this quadratic equation: px squared plus qx plus r is equal to 0, where x is a real number. Of course, here x is also a real number. Now, the roots of this quadratic equation, px squared plus qx plus r is equal to 0, they are real if and only if q squared minus 4 times p into r is greater than or equal to 0. If q squared minus 4 times p into r is equal to 0, both the roots are real and equal. If q squared minus 4 times p into r is greater than 0, both the roots are real and distinct. Of course, if q squared minus 4 times pr is less than 0, then the roots are going to be imaginary. Both the roots are imaginary. This term q squared minus 4 times pr is called a discriminant because it discriminates, it distinguishes the nature of the roots, whether the roots are going to be real, which happens when q squared minus 4 pr is greater than or equal to 0, whether the roots are going to be equal, which happens when q squared minus 4 pr is exactly equal to 0, the roots are going to be equal and real, or whether the roots are going to be imaginary, which happens when q squared minus 4 pr is less than 0. That's why it's called the discriminant. Now let's look at plugging the values of p, q and r for this given equation here. So here p is a squared plus b squared, q is minus 2 times b into a plus c, and r is b squared plus c squared. Right? So let's plug these in here. So this equation will have real roots, which is what we are supposed to prove. We are supposed to find the condition under which this equation, this quadratic equation, would have real roots. Now q is minus 2 times b into a plus c, right? This the whole squared minus 4 into p is the coefficient of x squared, which is a squared plus b squared, plus r is the constant term here, which is plus b squared plus c squared. Right? This needs to be greater than or equal to 0 for this equation to have real roots. Now we can expand this to squared. Minus 2 to the whole squared is just plus 4 b squared into a plus c the whole squared. This needs to be greater than or equal to 4 times a squared plus b squared into b squared plus c squared. Now we can divide both sides of this inequality by 4. Nothing changes. It's just a positive number. And now we can expand this. So this is b squared into a plus c the whole squared is a squared plus 2ac plus c squared. This needs to be greater than or equal to, we expand this side by opening the brackets, a squared plus b squared plus a squared into c, a squared into b squared plus a squared into c squared plus b power 4 plus b squared into c squared. So we simplify this, we get a squared into b squared plus twice ac times b squared plus b squared c squared needs to be greater than or equal to a squared into b squared plus a squared into c squared plus b power 4 plus b squared c squared. Now b squared c squared, we can cancel them because they are the same number on either sides of the inequality as is a squared b squared. So this equation, this given quadratic equation would have real roots if and only if 2 times a into c into b squared is greater than or equal to a squared c squared plus b power 4. So we take this to the other side. This, in other words, this quadratic equation would have real roots if and only if b power 4 can be written as b squared the whole square. Now this plus 2a is ac times b squared. When it goes to the other side, it becomes minus 2 times b squared into a into c plus ac the whole square. This needs to be, because it's on this side, needs to be less than or equal to 0. Right? Now let's try and factorize this expression. B squared the whole square minus twice b squared times ac plus ac the whole squared. We know that x minus y the whole squared is simply x squared minus 2xy plus y squared. Now if we look at this expression and this one, if we took x as b squared, then x squared would be b squared the whole squared. And if we took y as a into c, then y squared would be a into c the whole squared. Minus 2xy would be minus twice x, which is b squared, times y, which is ac. So this perfectly fits into this formula. So basically this can be factorized as b squared minus ac the whole squared, and this needs to be less than or equal to 0 for this given quadratic equation to have real roots. Now we are given that a, b and c are real numbers. So b squared is also going to be a real number, ac is also going to be a real number, b squared minus ac is going to be a real number, b squared minus ac the whole squared is also going to be a real number. Right? And we know from the properties of square numbers that the minimum value that a square of a real number can have is 0. So b squared minus ac being a real number, its square can never be less than 0. Right? So as b squared minus ac is a real number, b squared minus ac the whole squared can never be less than 0 for any set of values of a, b and c, real values of a, b and c. So the only possibility is b squared minus ac is equal to 0. Right? Which means that a, b and c have to be in geometric progression. That's the condition that we are supposed to prove. If and only if, that's why the question says IFF. It's not just IF, it's IFF, if and only if. So only when b squared is equal to ac, this equation, given quadratic equation, can have real roots. What's more interesting is that it will have equal roots in this case, because the discriminant is going to be equal to 0. Right? Discriminant can never be greater than 0 in this particular case. It's either going to be less than 0 or equal to 0. So when b squared is equal to ac, the discriminant is exactly equal to 0. So the given quadratic equation would have equal roots, which are also real, only when b squared is equal to ac. Hope you like this problem and its solution. Please subscribe to our channel and look at our previous videos as well as our interesting future videos as well. Thanks for watching.